are they here? Oh, okay. So I shall introduce myself. My name is Leslie. My name is Leslie Banks-Sills, and I'm a professor emerita at Tel Aviv University in Israel. And I thank Alexander for everything, for inviting me to present to you today, and for all of the work he's done for ECF 22. I'm sure we're going to have a wonderful conference. I guess I have a mic. Can you hear me without the microphone? Okay? Oh, not so. Okay. So I'll try to talk to the microphone. He's done a really great job in preparing us for ECF 22. I'm also the president of ESIS, so unfortunately or unfortunately, you're going to be seeing a lot of me opening the conference and closing the conference. And so I won't talk about that. I will start to talk to you about interface fracture mechanics, and I'm honored to have Jim Rice here, who is really responsible for a lot of the things that I'm going to say today. So I'll mention him every once in a while. So let's get started. Okay, we're going to begin to talk about interface fracture mechanics for two dissimilar isotropic homogeneous materials. Later on, we'll talk about some anisotropic materials, but this is how we'll start. And I'll present to you the stress and displacement fields in the neighborhood of the crack tip. We'll talk about something called the oscillatory parameter. I'll give you a bit of a historical perspective after you understand a few things. Then we'll talk about, we take the stress intensity factor, which is a complex quantity, and we normalize it to get rid of the inherent complex nature of it. We'll talk about the interface energy release rate and phase angle, a failure criterion, how we calculate stress intensity factors, and in particular I'll talk about a conservative integral called the M integral or the interaction energy integral. Then we'll talk about testing, and I'm going to talk about the Brazilian disc specimen made of glass and epoxy and made of 2 ceramic clays. And then we'll talk about deterministic and statistical failure curves. So I'm going right in, and you look at that and you may get a headache, but try to follow me and I'll try to lead you through it. And if you miss it a bit, you can still understand about interface fracture mechanics. So we talk about 2 materials. Material 1, which has shear modulus mu1, Poisson's ratio nu1, alpha 1 is the coefficient of thermal expansion, and in the lower half plane we have mu2, nu2, and alpha 2. And so we have an interface that's a perfect bond, and we have a crack going along the interface. And this is a little confusing to me to have two boards, but we have an upper material, material 1, and a lower material, material 2, and there's a bond, a perfect bond, so there's continuity of displacements and tractions across the bond, and we have a crack which is traction-free or stress-free along the interface. And K symbolizes the upper and lower materials 1 and 2. So we have stresses for the upper material when K is 1, and stresses for the lower material when K is 2. And that affects these functions, sigma 1 and sigma 2, which are very well-behaved functions which have analytic expressions, which I will show you in the coming slides. So K appears on sigma 1 and sigma 2, and on these stresses sigma. And alpha beta is 1, 2. So we're talking about the in-plane stresses, sigma 1, 1, sigma 2, 2, and sigma 1, 2. And now we have something which may seem a little strange to people who know fracture mechanics and know about mode 1 and mode 2. We now have a complex stress intensity factor And they don't have the normal units that we know from isotropic homogeneous materials, and I'll say more about that as we go. So K appears in this expression and the second expression. This is the real part of this expression. This is the imaginary part of the same expression, and I is the square root of -1. And so there's K. And then we have this parameter, epsilon, which is called the oscillatory parameter, and it's related to the mechanical properties through the shear moduli and through this parameter kappa, which is related, depending on plane strain and plane stress, to Poisson's ratio of the upper and lower material. And I'll say more about epsilon when we go and look at the values that it takes. So we have stresses which depend on R. So we have the square root singularity that we're used to for isotropic homogeneous material, and I'll turn over here. And then we have R to the I epsilon. So R to the I epsilon, we're looking at this expression as R goes to 0. So the stresses are going to 0 as 1 over the square root of R. So they're not going to 0, they're going to infinity as 1 over the square root of R. And they're modulated by, they're modulating this R to the I epsilon, which is as R goes to 0, it oscillates wildly. And I'll show you a little cartoon figure about that. And as I said, we have the real part of this quantity and the imaginary part of this quantity. And then we have these functions sigma, which are just functions of, they're trigonometric and hyperbolic trigonometric functions of theta and epsilon. And we'll talk about that. Okay, so here's K, and what are the units of K? Stress has normal units. It's not complex, mind you. Sigma 1 and sigma 2 are real quantities, and here we're taking a real quantity and an imaginary quantity. So there's no, sigma is just an ordinary stress, which has functions of force to length squared. And so if you go through this, you can see that K has functions of force times length to the -3/2, which is what you usually expect for a stress intensity factor. But then we have this L to the -I epsilon, which is maybe a little bit uncomfortable, and we have to learn how to live with it. So we learn how to live with it. I just note that when we change the units, for example, if we want to go from a length unit of millimeters to meters, it's not that K1 and K2 change proportionally. Because of the units, which are L to the -I epsilon, the ratio of them does not stay the same. It changes. So it's a little bit strange, and one has to learn how to deal with that. Now, we can also have an out-of-plane stress field, and again, we're talking about, and I didn't say, linear elastic and isotropic materials. So in this case, we have, I can use this. We have again that K equal the lower case K equals 1, 2 is for upper and lower materials. And then we have stresses sigma 1, 3 and sigma 2, 3. And we have the behavior 1 over the square root of R. It's the same thing like homogeneous isotropic material. And then we have a mode 3 stress intensity factor, which represents mode 3. It's the tearing mode, or it's the out of plane shear mode. And then of course we have this expression, and epsilon does not appear here, you can see. So now, if you didn't have a headache before, you have a headache now. This is the same expression I showed you before, where alpha beta is 1, 2, K is 1, 2, I is the square root of -1. Here's the complex stress intensity factor with its crazy units. And here's the oscillatory parameter epsilon. And now you can see these functions in an explicit way. So you have sigma, I can't even see it from here, So it's sigma, you have, for the upper material where the 1 precedes the symbol, you have sigma 1, sigma 1, and sigma 2, representing the stresses in the 1, 1, and 2 directions. And you can see that although maybe it looks a little complicated, these are easily evaluated functions. We have sinh, and we have exponential, and we have cosine and sine, so they're quite nice. So we have very nice analytical expressions, and then that okay. These are the functions too. If you recall, there's sigma 1 up the superscript 1, and sigma 2, the superscript 2, so this is 1, 1, 1. And then the next one, there's 2, 2, 2. And here are the out-of-plane stress functions. And this is all for the upper material. There's a 1 before each of these expressions. And if we want the expressions for the lower material, all we have to do is substitute minus pi for pi when theta is less than 0. So theta runs from minus pi and then jumps over the interface and goes to plus pi. And so when theta is negative, then we substitute in these expressions for pi, we substitute minus pi. So it's quite simple. So the function's a little complicated. I'm happy to see that you have you have my slides, so that's great. Okay, so let's talk a little bit about the stress singularity because it's a little strange. So if we take the previous expressions and we take theta is equal to 0, we get a very nice, neat expression. We have k r to the I epsilon divided by the square root of 2 pi r. So we have the square root singularity, and then we have this oscillatory part. And I think if you remember what the units were, because k has units of length to the minus I epsilon, you can see that that is canceling out here. And so the stresses are quite nice. There's no problem with the stresses. So here's the stress singularity as I just mentioned. And let's look a little bit about the mathematics, how we deal with the stress singularity. Okay, if we take r to the I epsilon and we write it as an exponential, so it's just an exponential and a log. So we have e to the I epsilon log r, which then works out to be cosine of epsilon log r plus I sine of log r. And if we took the absolute value of this, we would get 1. So the magnitude of this expression is just 1. Okay, and I'll mention that again. So as r goes to 0, if we look at this expression, log of r is going to minus infinity. So, and cosine and sine are bounded by plus minus 1. So this is just going to infinity. It's just oscillating more and more wildly. The infinity is being caused by the 1 over the square root of r. So it's going to infinity as 1 over the square root of r, and then it's going back and forth between plus 1 and minus 1. So that, and I will talk about the history of all this, that is one of the things that stopped, I believe, people from working on interface fraction mechanics for a long time, and I'll get to that, because this was very, very troublesome. There's something even more troublesome, which we'll see. We're going to look at the displacements, the crack face displacements, and they also oscillate, but when they oscillate, they interpenetrate. The upper crack face goes mathematically into the lower crack face and vice versa. Of course, that's not physically tenable, and so what you really, if you want to do something physical, you have to assume that you have contact here. That's physically what would happen. But anyway, we can live with it, and so we say that we have an oscillating square root singularity. So now let's talk a bit about fracture modes. You're used to mode 1, mode 2, and mode 3. in linear elastic materials which are homogeneous and isotropic. So mode 1, the crack opens. Mode 2, the crack slides in the plane. And mode 3, the crack slides out of the plane, the tearing mode. But here, we don't have that behavior. So let's say we take K20. If we took K20 and we had a homogeneous material, we would have K1 and we would have opening. And we would only have sigma YY along this line. Okay, so if we take this expression and look at it again, and we're going to take K2 is equal to 0, so K is real, it's only equal to K1. And if we write this out in a longer form, we have a real part and we have an imaginary part, and we're looking along the interface. So in this case, we have both opening, well, we have tensile stress here, but we also have a shear stress. So this is different from linear elastic isotropic materials, where when you take K2 is equal to 0, you only have sigma 2,2 along this axis. Sigma 1,2 is equal to 0. So you can see maybe to say, well, epsilon, we don't know yet, but I'll tell you ahead of time, epsilon is a small quantity. So this component is generally, of course, R is going to minus infinity, but this component is generally smaller than that component in the case when K2 is equal to 0. Okay, so let me look over here, and again, as I said, for homogeneous material, if K2 is equal to 0, then K21 on theta equals 0 is 0. But K1 and K2 no longer represent the opening and the in-plane shear modes, as they do for linear elastic isotropic homogeneous material. So now let's look at the in-plane displacement field. And again, I give you a bit of a headache, I suppose. The expressions look complicated, but let's break them down a little. Again, K represents, K equals 1 is the upper material, K equals 2 is the lower material, and I guess I'm going too fast. The displacements are going to 0 along the crack faces as R goes to 0. But of course, then we have this oscillating contribution, and we also have the out-of-plane displacement field. And so again, we have expressions for the displacement. So you have in your laptops or your iPads, you have the expressions which are manageable. I'm sure everybody in this room can manage with these expressions. So let's take a look at what happens when we look at the difference from the upper face, theta is equal to pi, minus the lower face, theta is equal to minus pi. And we get this expression, which is not the simplest expression in the world, but it involves epsilon, and it involves the cosh of pi epsilon, and then it involves the mechanical properties in the terms of E bar, which you can see depend on plane strain and plane stress. And then we have the square root of R, which is driving this to 0. And we have the oscillatory behavior. So we're just going to look at delta U2. Delta U2 is the physically, it's the opening. Forget about oscillatory parameters and so on. Delta U2 is just the opening of the crack faces, because we're looking at theta is equal to pi and minus pi. And so we have this, in addition to all of this outside stuff, we have the real part of this expression. So let us look at what the real part of that expression is. We have, and so you see everything is real. So we have K1 multiplied by a complex looking expression. It's not complex, a complicated expression, and K2 multiplied by a complicated expression. And as R goes to 0, the log of R goes to minus infinity. So what we're doing is we're getting these oscillations, and these oscillations indicate interpenetration. The crack the crack faces above the solution shows that it goes into the material below. Mathematically, you can write that. Physically, it can't happen, so there has to be contact. And one of the things you need to know is how large that contact zone is. By the way, I didn't say this at the beginning. Anyone who has any questions, you're welcome to ask the question as we go. Don't sit there and have something really bothering you. I've gone through a number of slides. Please ask questions and slow me down, and so you're not sitting there wondering about something. I mean, it's not a class that we're coming back next week and we can go over it again, so do stop me. Okay, so what I was talking about is we have an interpenetration zone, but eventually it ends and then the crack opens, and it really depends on the value of epsilon. Well, it depends on two things. It depends on the value of epsilon, and it actually depends on how much shear is in the problem. If you have just tension, you have a large body with an interface crack and you put the body in tension, this zone will be very small. But people didn't know that, I think, initially, and so this interpenetration zone really was very troubling at the beginning. And you notice there's a C there indicating the C in my mind for contact. If you calculate the interpenetration zone analytically, which you can do, and you do a finite element analysis and allow contact elements to be along the crack faces, you'll get a different zone. The interpenetration zone is generally larger than the actual contact zone, but you need to worry about that. You need to take that into consideration. So now let's talk about the oscillatory parameter, epsilon, which is a function of the mechanical properties, depending on whether we have plane strain or plane stress. So if we divide the numerator and the denominator of this expression by mu2, we have this expression. And let's assume that material 1, the upper material, is made of cork, you know, what you put in a wine bottle. And for that case, nu is approximately 0, and E1, the Young's modulus is small. And let material 2 be alumina, which is a ceramic, and it's very stiff. And so mu1 to mu2 goes to 0, so these two terms drop out. And kappa is equal to 3 in both cases because nu is equal to 0. And so kappa is 3, and if we substitute 3 in there, we have that epsilon is 1 over 2 pi the log of 3, which is 0.175. And that's the absolute value of epsilon. Epsilon can also be negative, but the absolute value of epsilon is less than or equal to 0.175. So it is small. It's not very large. And here I write it as the absolute value. The way that you get the negative one is just flip the materials. These two flip, and so you get a negative value for epsilon. So if it was positive, you can get it negative by reversing the materials. And here are some examples. And I believe this was taken from Rice's paper. A lot of this was taken from Rice's 1988 paper. So here we have silicon and alumina. I'm not exactly sure how I would put them together, but assuming that they're together and I don't have an epoxy interface, I'm not gluing them, I'm fusion bonding them, so to speak. So here's epsilon is very small, 0.075. And as you go down, in the last case, we have gold with magnesium oxide and 0.004, which is very small. And in fact, there's a paper by John Hutchinson in 1990, where he says, let's ignore epsilon. But I don't ignore epsilon. We continue to take epsilon into consideration, and everything works out well. Okay, so let's get an example of a stress intensity factor, something that we can maybe hang our hat on. So we're going to take an infinite body, which has two different materials bonded, and a Griffith crack, a central crack of length 2a, and we apply a stress, a tensile stress, perpendicular to the crack faces. And I'll talk about sigma 1 and sigma 2 in a few minutes. So the analytical solution was obtained early on in the 60s. The analytical solution for K is given as this expression. And for a moment, if we just assume that the two materials are the same, epsilon will be equal to 0, so this term goes out. This term, the 2I epsilon goes out, and so what you're left with is what you normally expect for a homogeneous material, sigma square root of pi a. Written in complex form, but it divides up. K1 is sigma 2 square root of pi a, K2 is sigma 1 square root of pi a. It's what we remember from homogeneous isotropic materials. So you note that sigma 1 is 0, and so we only have tensile loading. We don't have shear loading far from the crack. And so we have now we have a complex stress intensity factor, just as we were speaking. Of course, epsilon is a small number, but K2 is not equal to 0. So if we have tensile loading, K2 is not equal to 0. So I want to, before talking about sigma 1 and sigma 2, well, maybe I'll talk about them. I don't know if I have a slide about them. It turns out that in order to maintain continuity of displacements along the interface, we have to, I do talk about it, we have to prescribe sigma 1 and sigma 2. And I'll tell you in another slide how we prescribe them. Okay. So here we go. This is our expression, and let us simplify the expression. So we have K1 plus IK2 is sigma 2 to infinity, square root of pi a. And now we have to simplify this. So I put a little note here for people who forgot their complex variables. And so suppose we have a complex quantity a plus ib. A and b are real. So we can write it as the magnitude, the square root of a squared plus b squared. And then we can write the rest of it as an exponential term, I tan to the arctan of b over a. So we can then use this expression of Euler, e to the I theta. We can write e to the I theta as cosine theta plus I sine theta. And so without simplifying it, we can get a plus bi into separate quantities. One has the cosine in it, the a, and b has the sine in it. Of course, if I start to figure out what all this is, I just get back to a plus ib, but I want this format. So that's for the complex variables. So if we go back here, we can then write K1 in terms of the cosine of these two, arctan of 2 epsilon and minus epsilon log 2a. And you can simplify this further, actually, but I'm not going to go into that. And K2, and I'm sorry about the board here, but it's a little cut. It's just the sign. The K2 is exactly the same expression with sign. So applying just tensile stress, we get both a K1 and a K2. Okay, so when x1 goes to infinity and x2 is equal to 0, I don't have any axes. So what I mean is when we're along the interface going into infinity in that way, and we want U1 of the upper material to be equal to U2 of the lower material, we then write a derivative of them in the x1 direction, they also have to be equal, and so therefore the strains have to be equal. The strain epsilon 1,1 along the interface has to equal epsilon 1,1 coming from the limit from the lower interface. And so if we use Hooke's law, and we'll take plane stress, so we'll assume that sigma 3,3 is 0, we get a relationship between the stresses in the upper half space approaching the interface from the lower half space approaching the interface. And so in terms of our sigma 1 and our sigma 2, we have a relationship between sigma 1 and sigma 2, which involves sigma 2,2 at infinity. And so then we have a relationship, here's the simplified relationship between sigma 1, sigma 2, which are these two tensile stresses. They don't affect the stress intensity factor, but we need to apply them to have this continuity condition. So we can choose sigma 2 anything that we would like. You can choose it 1, and then you can figure out what sigma 1 is. And if you were running a finite element problem, you would have to, and it's an infinite body, you would have to do this. If it's a finite body, you don't have to do this. Okay, so I said choose sigma 2 and calculate sigma 1. So now I'd like to give you a bit of a historical perspective to put things into perspective. If I remember correctly, in 1957, it's not written here, there are the papers of Irwin and Williams, which talked about the square root singularity, got the first term of the asymptotic expansion for a linear elastic homogeneous isotropic material. And then Williams in 59 goes on and he gets the stress singularity for interface fracture. And then we have a whole bunch of papers in 62, one by Sharapanov from Russia, England, Erdogan, Rice, and C. So in 65 we get a bunch of papers getting the stress intensity factors for different cases. They looked at different cases, they got the stress intensity factors, and then suddenly things go dark. It's like the Middle Ages of interface fracture mechanics. Nobody says anything. It's like they all got silent. Nobody told me, but I think, and I think you can confirm it, I think they got silent because this interpenetration, I mean, you know, it doesn't, what is this nonsense? The crack faces interpenetrate. Who can deal with that? So things got silent, and then Maria Komnenou from the University of Michigan wrote a series of papers, one with her student Schnauzer, I think it's Schmauser, it's an M, and the other with her thesis advisor, Dunders, where she assumes, I don't have a picture here, but she assumes that there's a contact zone. In other words, there's an interface, there's a contact zone, and then the crack opens up. And what she's looking for is she's looking for the size of the contact zone. So in the first paper where it was tensile loading, she finds that the size of the contact zone is between 10 to the minus 4 and 10 to the minus 10, the crack length, or the half crack length. She does a Griffiths crack. She has a central crack and an infinite body along an interface. And it depends on the values of epsilon, on the value of epsilon, whether it's 10 to the minus 4 or 10 to the minus 10. Well, if it's 10 to the minus 4 times the half crack length, that's fine. I mean, who cares? It doesn't, it's certainly within any sort of nonlinear small-scale zone that you could possibly have. But then she goes on in the next paper in 1978 to look at a crack that the body is in shear. The same body, two materials, a finite length crack. And at one side, she finds basically the same thing for tensile loading, but on the other side, she finds that the overlap, the contact zone, it's not overlap, that the contact zone is about a third of the half crack length. So that's serious, but at least she's quantified it for us and she's given us a hint. The hint is that it depends on epsilon and it depends on the loading. So if you have tensile loading, you're probably safe. If you have some shear, you're probably okay. If you have a lot of shear, you're in trouble. And the paper with Komnenu and Schmauser, I think it's Schmauser, did a combination of tensile and shear, and she looked at that. So people woke up. Okay, so as I say here, she assumed that there was a contact zone, and she examined it. And then later on, they wrote a whole bunch of papers where they looked at 3 different zones. There was a sliding zone and a contact zone and all kinds of interesting things that they did. But I think they sort of solved the problem. They said, okay, you can use it, but just be careful. Look and see how big your zone is in the physical problem that you have. So then we come back with Rice, Swow, and Wang, and Hutchinson telling us how to treat the problem. And so if you look at I saw the 1988 paper of Jim Rice, that there you can learn just about everything you need to know, and you can walk out of the lecture right now. You don't need me. Okay, so they reestablished the singular field for small-scale interpenetration. That is, we have a small zone of interpenetration, and we can neglect it. Just as we neglect a small-scale plastic zone, we can say all the nonlinear effects are in this zone. But of course, if you have a lot of shear, you have to be careful, and you have to see how large the zone is. And then I noted a whole bunch of papers in which tests were carried out. There are many more than just these. Lichty, with many people, wrote, he's in this paper with Swedner, and he has quite a number of papers, and I and many of my students have papers. Zenda from Cornell wrote papers, Swow from Harvard. Okay, so you can find many papers on testing. There are many more than I've written here. So that gives you a bit of a historical paper, how we got to today. So now people worried about this stress intensity factor that had these crazy units of L to the minus I epsilon. So you can normalize it with this factor L hat, which is arbitrary. You can choose it anything you like, but I have some advice. If you're carrying out a study in which you're looking at the effect of crack length, don't choose L as the crack length, because if the crack length is changing, then your units are changing. So pick L to be a meter, to be a centimeter, to be a millimeter, to be a micron. Pick it to be something, and then you can follow through, and you can vary your crack length. If you're going to carry out tests, we've used L as a free parameter in the test to fit the data and the criterion well, and I'll talk about that. So L hat is a free arbitrary parameter at this point. And now we can, I keep pushing the wrong button. We can now define a phase angle, psi hat, which is the arctan of the imaginary part of k hat. So it's KL hat I epsilon divided by the real part. So this is basically K2 hat versus K1 hat, and this is a phase angle. And we can now manipulate K hat. It turns out we can write K hat as the absolute value of K, e to the I psi hat, our phase angle. The absolute value of K, the sum of the squares of K1 and K2. And if we look at L hat, if we go back here and we write what L hat is, L hat to the I epsilon, we can write it in terms of cosine and sine. And then the absolute value of, since this is cosine and sine, the absolute value of L hat is 1, so the absolute value of K hat is equal to the absolute value of K, or the magnitude of K hat is equal to the magnitude of K, and that's why in this expression I can write K hat or I can write K. It doesn't matter, it's the same. And I remind you about sigma 2,2 and sigma 1,2 along the interface. Theta is equal to 0. And so I can also say that psi hat is the arctan. If I substitute in here that the distance r is L hat, then these two expressions are in agreement. We have the arctan, we have the arctan of sigma 2,1, the shear stress, divided by the tensile stress along the interface at a distance of L hat from the crack tip. That's what that expression says. Okay, so now let's talk a bit about the phase angle. Let's say that we take two expressions. We write that K1 is related to L1 hat, and K2 hat is related to L2 hat. It's just from the expression we had on the previous slide from here. And so K1 hat can be written in this way, and K2 hat can be written in that way, and we can solve for K in both cases. And so this is the expression for K1 hat, which I expand over here, and this is the expression with K2 hat, and they're equal. So we have a relationship between psi 1 hat and psi 2 hat through L1 hat and L2 hat. And if we write it in terms of an exponential, we have a relationship which we now see that we can go from one psi, and I guess I'm missing a hat here, we can go from one psi to another through a ratio of the L's and epsilon. So what this does, if psi will be, let's say, our abscissa in some plot, we can translate the abscissa by changing the value of L. And we use that, it's quite useful. So it's simple to transform from one length scale to another. Okay, well, let's go back. We want to estimate now, the size of the contact zone. My daughter who teaches told me that after 15 minutes, everybody goes to sleep. And you should wake everybody up, like by asking a question or something. So maybe you can ask me a question. Let's wake up, because this is heavy stuff. I know that this is heavy stuff. In fact, when Alexander took a look at this, he says, "This is what you're teaching?" It's too hard. So I hope I haven't lost 50% of you or 90% of you. Anyway, one of the things that bothers us is this contact zone or interpenetration zone, which occurs here. So we're going to look for the largest value of R for which delta U2 is equal to 0. When delta U2 is equal to 0, we are beginning an interpenetration zone. So we go back to our complex expression for delta U2, which I showed you earlier. And so we want to know when delta U2 is equal to 0, and so that we have interpenetration. And so basically, we're going to look at when the real part of this quantity is equal to 0. And so we can rewrite in a simplified form with the L, we can rewrite K. So we've rewritten this expression, and I remind you that K is equal to K hat L hat to the minus I epsilon. And so that's how we get this expression over here. And we now can write this in terms of an exponential when we manipulate this, as I showed you, and manipulate e to the I psi hat and L hat, R and L hat to the minus and plus I epsilon. And so we're interested in when delta U2 is equal to 0, so this expression has to be equal to 0. And so we need to take the real part of this, and the real part would be the cosine of the argument in the exponential. And so when this cosine is equal to 0, then we're going to have the largest value. We're going to have interpenetration. It's really not the contact zone, it's the interpenetration zone. It's the value, the largest value of R. And for epsilon greater than 0, the largest value of R is found when the cosine is equal to minus, the argument of the cosine is equal to minus pi over 2. And so if you manipulate this, this is the expression for RC. So RC over L hat is this exponential expression, and epsilon is positive. So it's, as this is driving, this is an exponential, epsilon is a small quantity which you can even neglect, and so this is what's driving it to 0. So RC is very small when this is large compared to epsilon, and epsilon is a small quantity. So as I showed you before, I'm showing you the same slide. We get crack face interpenetration for this RC that we found on the previous slide. We can also ask the question, we can ask this, with the same expression, we can ask the question, for the crack to be open, what values are we going to have for R? So we now are asking the question, when is delta U2 greater than 0? And so again, we're asking the question, when is this expression greater than 0? And it will be greater than 0 from our previous slide when this cosine term is greater than 0. And so we can bound it between minus pi over 2 and plus pi over 2. And I'm taking here that epsilon is greater than 0. And so we can write this, and we're finding what psi hat is for the crack to be open. And so we have these two expressions, and we're going to take R smaller than A over 10. A is half crack length. Epsilon is small, so we'll write tan, arctan of 2 epsilon is 2 epsilon. And so here is our expression. I can't see it over there, but I can see it over here. So it's in terms of A over L hat. L hat is this arbitrary length parameter. I can choose anything I like. And I'm going to neglect, I'm going to neglect this term. I'm going to be more conservative. This just decreases the value. And so if I take A over L to be 100 and epsilon to be 0.06, which was the parameter in Lechty's work for epoxy and glass, I find that psi hat, the crack will be open if psi hat is between minus 83 degrees and 87 degrees. And so in that case, I have a K-dominant zone, and inside I have a small zone where I have this interpenetration, and I think of it in terms of small-scale yielding. We go until 1:45. Okay, so we need a lot of stretching. Okay, so we've looked at the stress and displacement fields. We've looked at the problem of the oscillatory parameter, which gives us stresses that are oscillating wildly as we approach the crack tip. We have interpenetration, and we have to make sure that that zone is small for this to be valid. We've looked at a phase angle, and now we can talk about the energy release rate. So we're going to talk about the interface energy release rate, not worrying that we actually have this oscillating business, but we have the square root behavior for sigma 2,2, and not worrying about the interpenetration, just forgetting about it and saying it's small, so I'll neglect it. And we allow for a delta A. We have a virtual crack extension, and so this is not the shape of the zone. One of my students said that's not good. No, the shape of the zone is more parabolic, but this is just a cartoon to see that we have the stress, and we have, with a virtual crack extension, we have this displacement. And to obtain the energy release rate, what we need to do is we need to calculate the work done in closing that part of the crack the delta A. We want to close delta A and calculate how much work, if we take this stress and we apply it in the opposite direction and we close this for a unit crack extension, or for crack extension delta A, we can calculate the work done in closing the crack. And that's equivalent to the energy release rate. So if we look here, that one of my students did for me because I couldn't do that. We closed the crack with sigma 2,2. So let's go back. So we have the crack has a delta A, and we're going to close this crack, and we want to calculate the work done in closing the crack. Only this part, he really needed to leave it open over here. This part is open, this part is closed. Okay, so let's look at the mathematics of it. So the energy release rate is the work done in closing the crack. So work, I have 1/2. And so I have sigma 2,2 going through delta U2. This is the mode 1 energy release rate, and this is the sliding, the mode 2 energy release rate. So, and it's for a unit crack extension, or for this delta A, this virtual crack extension delta A, and we take delta A going to 0 and we get the energy release rate. So we have the energy release rate for both opening and sliding crack faces. Now if we want to go to interface cracks, and so I put this little I here for interface, it's not so easy to get this expression. I want to get this expression separate. So the way you do it with a little trick is you take the real part of this quantity. So when you multiply sigma 2,2, you get it by delta U2. Here's that expression. I times I is -1, so with a minus, that's a 1. And so we have sigma 2,1 multiplied by delta U1. And so we just take the real part of this and we get the interface energy release rate. And if you work a bit, you can show that GI is just the sum of the squares of the stress intensity factors, where H is related to the mechanical properties, E1 and E2 bar, and epsilon. Epsilon is also related to the mechanical properties. So you can think of this as a Young's modulus type quantity. And so you have the interface energy release rate related to the stress intensity factors. And you can then go on to show that J, the J integral, is equal to the interface energy release rate. Okay. They're both equal to the sum of the squares of K, K1 and K2. Another aside, another parameter that you may find in the literature are Dunder's parameters. We have alpha, and it's not the same alpha. This is the coefficient of thermal expansion, and this is Dunder's parameter alpha, and beta. He has two parameters. In terms of the shear moduli and kappa, I don't know if yes, here's kappa, for plane strain or for plane stress. So we have alpha and beta. And so we can write epsilon, not as we wrote it before, but we can write it in terms of beta, and sometimes this is useful to have. And alpha, interestingly enough, can be related to these Young's moduli parameters. And so I show you what the E's are in terms of plane strain and plane stress, and I'm sure you're familiar with those expressions. Okay, and alpha is between -1 and 1, and then for plane strain and plane stress, you find two expressions for beta. Okay, next, we're interested in having a failure criterion. I mean, when you do fracture mechanics, you do homogeneous isotropic material, the first thing you want to know is you want to know what is the stress intensity factor of the body. So you go and you solve by finite elements, for example, for a variety of crack lengths, and you find K as a function of crack length. But then that doesn't tell you when the crack is going to propagate or under what conditions the crack is going to propagate. So you know the stress intensity factor, which means you know the stress field in the neighborhood of the crack tip, assuming that you have small scale plasticity, and then you need a criterion. So the scientists, engineers came up with a criterion. When K1 reaches K1C for node 1, the crack will propagate, and then you can find what would the crack length be, what would the applied load be, the applied stress. So that's what you do for homogeneous isotropic materials. Well, here we need a failure criterion. We don't know how to find the stress intensity factors yet. But we know what a stress intensity factor is, and we know how the stresses look and how the displacement looks, and we know that we have an interpenetration zone, which is a headache, and we have to deal with it. We have to find in our particular problem how large this interpenetration or contact zone is, and it has to remain small for this philosophy or this mathematical paradigm to be used. So we need now a failure criterion. I'll give you the stress intensity factor. Tell me, is this going to fail or isn't it going to fail? So clearly it depends on material. So let's take a look at how we can get a failure criterion. And we start, there are quite a number of them. The failure criterion that I'm going to show you is the one that we've been using at Tel Aviv University. So we start off with the interface energy release rate. We're only looking right now at an in-plane problem, and we know that K1 squared plus K2 squared are equal to the Hack quantities, the normalized quantities without the epsilon in them, and so we can rewrite GI. And I remind you the relationship between K and K hat in terms of L hat, and I remind you the expression for H, and if you factor out K1 squared, you have a coefficient, and you have 1 plus K2 squared over K1 squared, which is none other than psi hat, K2 over hat over K1 hat, here it is psi hat. So we have tan squared psi hat, and we define G1C as K1 hat squared over H. And so this expression in blue is our failure criterion. And I have to, of course, tell you how it works. So we carry out fracture toughness tests, and I'm going to show you tests with what are called Brazilian disc specimens. You can use whatever specimen that you think it will be useful for you. We obtain the critical load at fracture and the critical crack length, AC. We calculate, and I haven't talked about this, I'll talk about this in a bit. We calculate K1 and K2 for that geometry, for the crack length, and for the applied load. And then we calculate GI, and we choose L hat. We then calculate psi hat, and I remind you what K hat is in terms of L hat. And we plot the points in a GIC psi hat plane. So we take we carry out 30 tests at different mode mixities. And we calculate GI, and we calculate for a specific L hat, we calculate psi hat. And we get a bunch of points that are in this plane. And if we take our expression, and maybe I haven't said exactly how to get every term, psi hat, we chose L hat, so psi hat is well determined. And G1C, we choose for each test, we choose K1 squared hat over H, we take the average, and we get an average G1C. So we say that when we have critical conditions, this is our G1C, which gives us GIC. And we see that the shapes are rather similar, but they don't match. So what we do is we go into our basket of techniques, And we remember that we can translate the psi axis depending on L hat. So we choose L hat. I mean, we do this in the computer. We change L hat, and this gives us psi 2. And now you can see this is psi 2 for L2. And now it fits it pretty well. And so we're able to translate this axis and get our data to fit this. And what does this curve mean to us? This is the failure curve. How do we use this failure curve once we've lined up the data? We say that we go into our structure, and let's say the structure is made, the interface is glass and epoxy, and we use the same conditions to make the interface in our specimen as the interface in our structure. And we measure the crack length, and we know what the highest load that this structure is going to endure. And we calculate psi, and we look for this particular L2 hat, and we look here on psi, and we see, is the GI that we calculate below the curve, or is it above the curve? If it's below the curve, then we're safe. And if it's above it, and I should have a safe, that's the failure curve. If we're above the curve, then we expect failure. And if we're below the curve, we expect it to be safe. And this is our failure curve, dividing between the failure and the safe zone. So I would say if we're on the curve, we expect failure. But then we have a problem when we look at this. We carried out tests, and some of the tests are below the curve, and yet they're lying in the safe zone. So this is scatter. This is what you have in tests. You always have scatter. You're not going to have all of the points lying perfectly on the curve. In fact, the way I drew these, they're even too good. You'll have some scatter down here and some scatter up here, so it's scatter. So in order to deal with the scatter, you have to do something statistical and say, let me demand that there's only a 10% chance of failure for a point below here with some confidence interval. So I have to do something statistical, which now I'm going to go into. Okay, I'm going to go into it, but I'm going to go into it later. So I'm going to show you briefly how we calculate stress intensity factors. Perhaps I should have done this a little bit earlier. So for all of those who know the J integral, and for all of those who don't know the J integral but will know it today after Professor Rice speaks, you can take the J integral and you can manipulate it into what's called the interaction energy, or the M integral. And it looks like this, and I guess it looks pretty complicated. So there are two solutions. There's solution 1 with the superscript 1, and solution 2. And of course, sigma ij has one expression in the, or one behavior in the upper half plane and one behavior in the lower half plane. And I haven't really done this. I can put little k's on all of these quantities, but in order not to make life too difficult. So we have two solutions. Solution 1, sigma displacement. Solution 1 is the sought after solution. I go to my computer and I solve finite elements and I get numerical values for them. And solution 2 is an auxiliary solution, which is the first term of the asymptotic solution. And I will be very specific. W, and I'll mention it down here as we go, is the interaction energy, interaction strain energy density, and I'll give you an expression. Delta is the chronicle delta, so when J is 1, delta is 1. When J is 2, delta is 0. And Q is a normalized virtual crack extension. Okay, it's complicated. You can't get this the first time. We make the calculation in a ring. If we're doing 2 dimensions, we make a calculation in a ring of elements surrounding the crack tip. Just as if this was a J integral, we would have a line integral going around. And of course, in the J integral, they don't have to match. And even in the M integral, they don't have to match, but here. But for convenience, this is a ring of elements that we take. And, all right, that's the ring of elements we take. Solution 1 is the sought-after solution. We obtain it with finite elements. Solution 2 is the auxiliary solution, which is analytical. And then we use superposition, so we have to have a linear elastic problem in order to carry out the M integral. Not so for the J integral. But we use superposition, so we combine the two solutions, the U's, the sigmas, and the epsilons. And the same thing with the stress intensity factors. And I tell you that W12 is either sigma 1 multiplied by epsilon 1 or sigma 2 multiplied by epsilon 1. And Q we write out in terms of shape functions. Those of you who are familiar with finite elements, we then have to choose this vector in 2 dimensions. It's has eight entries, Q11 to Q18. And this gives us the virtual crack extension. And if you want to know how to use it, we've written a lot of papers, and you can see how we do that. And we can show that there are 2 expressions for M. One of them is the integral, which we integrate numerically. And the other one is related to the stress intensity factors, and it comes out of when we said J or G with the sum of the squares of the K's. But now we have this middle term, which gives us K1 times K2 and K21 times K22. So we choose the K's judiciously. Those are the unknown stress intensity factors. And then we need 2 equations, and we use 2 auxiliary solutions. Solution 2A has K12A1 and K22A0, so that if we take this expression, we now find that M12A is just equal. We have separated out K11. So we do the numerical integral, and we find K1. And we do solution 2B, we do the trick the other way, and we have K2 separate. From what I have told you now, you cannot go and do it. I mean, you really have to know how to do it. Abacus has the M integral for 2 isotropic materials. Abacus does not have the M integral for 2 anisotropic materials. That you have to write yourself. Now, as far as the auxiliary solutions go, where we have 2A, and where K1 2A is 1 and K2 2A is 0. Oops. We substitute for K 1 here, and I'm talking about 2A, and 1 here. So these are the expressions, and I showed you these expressions. We have them, and I think I have them on the next slide. Maybe not. That's the other one. And I guess we don't. We don't have them here, but you can easily write them. And all I want to give you the message from this is that there are ways to get the stress intensity factors. The M integral is one way. There are other ways of doing it. You can do displacement extrapolation. You can do virtual crack closure technique. There are other ways as well. There are many ways that you can do this. This is just one way, and so I'm just telling you that if you want to calculate stress intensity factors, the literature is rich, and one of the ways of doing it is with the M integral. So I think at this point, we have 5 minutes to go. I think I'm going to stop here as a good stopping place and ask if anybody has any questions, which now puts you guys on the spot. Thank you. A question.
Could you please explain the basis of this consumption? So we have 2 Ks for one material and for another, and you apply this imaginary and real mathematics. And what is the basis of this assumption? Is it experimentally proved that you have this, for example,
analytically solve the problem, just like for a Griffith craft in a homogeneous isotropic material, you can use different techniques, integral equations, complex variable technique like Bush-Feely, and you can find that K1 is equal to sigma square root of pi a. You can now do this with interface cracks where you're going to have to match the boundary conditions or the continuity conditions along these crack faces, the stress and infinity. And analytically, I showed you a case solution. That analytical solution was obtained. To find the asymptotic solution, in other words, maybe I'll go back and I'll be very specific. This is not found experimentally. To find this form of the solution with the with these exact expressions, you have to do asymptotics. It's not trivial. It's very complicated, but we have it. We have it. So analytically, this was found. This was found analytically. And then if I go on and I show you a stress intensity factor, okay, this was analytically found. This is not experimental. Somebody sat down a pencil and paper, lots of paper, worked very hard, and found the solution. But they found it for us. And so we know that we have this behavior. And then we want to interpret what all of this means. So if you go back to the stress behavior, it's in the neighborhood of the pressure. There are, just like in isotropic homogeneous material, you have higher order terms. You have R sigma is R to the minus 1/2, and the next term is the T stress R to the 0, R to the 1/2, and so this also, not this, but the stress field and the displacement field have higher order terms. So in the neighborhood of the crack tip, we have this behavior, and so we're sort of going over from isotropic homogeneous material to two isotropic materials. And so we have all of this analytically, but then we have problems with it because, first of all of a sudden the stresses are not just going to infinity as 1 over the square root of R, they're oscillating wildly. So we have to interpret that. And as long as we keep this contact zone or interpenetration zone small in our specimen or in our body, and we examine that it's small, we can use all this mathematics.
But what about the experimental part? I mean, this zone, the self-penetration zone, I think it's...
Okay, after the break, I showed you a fracture criterion, and after the break, I'm going to show you I'm going to show you testing. And I'm going to claim to you that we examined the interpenetration zone. We put contact elements and we looked. And so I will talk to you about that after the break. Okay. Yes. The M integral, we don't look, we have calculated the M integral in the elements close to the crack tip, the 4 elements surrounding the crack tip. And actually, we don't get very good values for it, but it's not, in my opinion, because of the oscillation. It's because we're using, even though they're 8-noded, I didn't say this, I will say this later. We use 8-noded isoparametric elements when we calculate stress intensity factors. And we move the nodal points adjacent to the practic to the quarter point, and we get a square root singularity. And when we do that with isotropic homogeneous material, not two materials, we're describing pretty well the square root singularity. But even so, we don't get great results in the 4 elements or the 2 elements if it's a symmetric problem next to the adjacent to the practic. So we're always going outside the zone, that zone. And so it probably will be, unless you have a very large oscillatory oscillating zone, interpenetration zone, you probably won't be in that zone when you're going outside. So we do go outside. It's really not a problem. You can see, you can do the calculation, and we don't just calculate in one ring. We calculate in like 7 rings, and we look at the difference, the path independence, and if it's not sufficiently path independent, we refine the mesh, and you know, we're checking ourselves all the time that we're getting the results.
And it is that because of the symmetry, does it control any particular number?
Because of
The symmetry of oscillation.
the symmetric,
Yeah.
I didn't understand.
In the oscillatory zone, because of the symmetry, does this term immediately does it converge to a particular number?
What I suggest is we've gone over time. Why don't we talk during lunch? Okay? Okay. Anything else? Pressing? Very pressing? Okay, so we meet back here at Alexander. We meet back here at
In 1 hour, exactly in 1 hour, be back.